In this lesson, we are going to be simplifying rational expressions. And rational expressions can look something like this or like this. And in grade 12, we're going to be graphing these. But in order to prepare for grade 12, we need to build the skills of simplifying them first so that's easier to graph. So by the end of this lesson, we should be able to simplify rational expressions. We're going to get into what a rational expression is in just a second. We're going to do that by factoring the numerator and denominator and then canceling out common factors. And by the end of the lesson, we should also be able to determine the restrictions on the variables of the rational expressions, and we're going to talk about that as well. So first off, what the heck is rational mean? Well, first let's start off with rational numbers. We've actually been using rational numbers since elementary school. They're just numbers that can be written in the form m over n, where both m and n are integers, so we can't have any decimals in there. So really it's just a fraction. So we have an example, 1 over 3, that's a rational number. It's a fraction. We have 1.25, that's a rational number because we can just write that as 5 over 4. And we have -4, that's rational because we can always write it as -4 over 1. So not every single number can we write as a rational number. A famous example is pi. There's no two numbers that when we divide them will make exactly pi. Another example is the square root of 2. That's an ugly, ugly decimal as well. There's no two numbers that divide and make the square root of 2 or pi. So now that we know what a rational number is, let's extend that to a rational expression. So rational expression is a fraction which the numerator and or the denominator are polynomials. So it could look something like this, like this. This is also a rational expression because we can put it over 1 like that. And there we go. Okay, so something that's very important to note is because we're dealing with fractions where the denominator is changing. So taking a look at this expression here, we can put in whatever we want for x, which means that this denominator is going to change depending on whatever x is. So we have to remember that when we're dealing with fractions, we know that we can never divide by 0. And if you forget, just throw 4 divided by 0 into your calculator and you're going to get an error. So it's undefined. We get an undefined answer when you divide a number by 0. So this important note is that a rational expression is not defined when its denominator is equal to 0. So that means for every rational function, we need to look at the denominator and ask ourselves, what is x not allowed to be? And to figure that out, we would say, well, what would the value of x be to make the denominator equal to 0? And then we know, okay, x is not allowed to be that. So taking a look at this example, well, if x was 0, then 2 times 0 is 0, and we'd be dividing by 0. So this means that x is not allowed to be equal to 0 in this example. So when we come up with our restrictions, graphically what it will look like is, one, it will either jump over the spot where x is equal to 0, and that's called a hole, or there will be an actual asymptote there at x is equal to 0, so that the function will approach it but never actually cross it. So let's take a look at these examples here. So for every example, we're going to state the restrictions on the following rational expressions. So for this example, we're going to take a look at our denominator. And just as a reminder, our numerator is allowed to equal 0. So we can take 0 and divide it by 2, and that just gives us 0. The problem is when we do 2 divided by 0. Then we get this undefined answer. So we're going to focus on the denominator here, and we have two variables in the denominator. We have x and we have y. So we're going to come up with restrictions for x and restrictions for y. Well, if x is equal to 0, then this becomes 0 times y, and the whole thing becomes 0. So one restriction that we have is that x cannot equal 0. And then on our y, it's very similar. If y is equal to 0, then the entire thing also becomes 0. So our second restriction is y cannot equal to 0, and we're done. Let's take a look at the next example. So again, we're going to focus on the denominator, not the numerator. This denominator cannot equal to 0. And it's pretty easy to guess the value that y cannot be. Y cannot be -5. If you ever get something complex though, you can always write it out and write out what the denominator cannot be equal to. So y plus 5 cannot be equal to 0. And you're going to just solve for y. So we have y is equal to, or cannot be equal to, we're going to bring this positive 5 over, and we have -5. So that's our restriction. Remember that the numerator is allowed to be 0, so we don't have a restriction on x. Let's work on this last one here. So we have this new rational function. We are going to restrict our variable in the denominator, so that's y. And if you can just check, we know that if y is equal to 3, then everything's going to equal to 0. So we have a very simple y minus 3 cannot equal 0, therefore y cannot equal 3. And there's our very quick restriction. So now we're ready to get into the good stuff, and we're going to start simplifying rational expressions. So here are a few steps that you can use to help you. So to simplify a rational expression, deal with the numerator and the denominator separately first. So simplify and factor the numerator. So if there's any terms to collect, do so and then factor it. And then if there are common factors in the numerator and denominator, we can cancel them out. What I mean by this is if I have 4, let's say, times 2 divided by 4. Well, 4 and 4 are two common factors in the denominator and the numerator. So 4 divided by 4, that's just 1, and we're going to be left with 2. And so if we have common factors, meaning everything's multiplying on the top and everything's sort of multiplying at the bottom, which really means division, then we can cross out these common factors. This is very different from this, 4 plus 2 all over 4. This answer is actually 6 over 4, which is equivalent to 1.5. But some students think, oh, we have common factors here, 4 and 4, and so I can cross them out and I'll be left with 2. But we know that this answer is not 2, it's 1.5. So the reason this doesn't work is because this is not factored up here. This is being added and subtracted. So if something is factored, everything all the terms should be multiplying against each other as well as in the denominator. So here that's what's happening, but here it's not. So remember that before you cancel anything out. Check if everything's truly factored on in the numerator and in the denominator, and that's the only reason why you can cross them out, because we're really dividing one into the other and we're going to get the answer of 1. So in the next examples, we're going to start simplifying these rational expressions, and we're going to do so with the tips we have on the previous page, which is we're going to factor the numerator, factor and simplify, then factor and simplify the denominator, and we're going to cross out any common factors in the numerator and the denominator. So we're going to simplify, and then we're going to state the restriction. So we can already take a look. You can already see that the restriction on this is going to be that t is not equal to 0. Okay, if t is equal to 0, then the denominator will be 0, and we'll get an undefined solution. So before we set restrictions for this, let's first simplify it. So I'm going to simplify the numerator and then simplify the denominator. So what I like to do is if I realize that I've got to do some simplifying, I'm just going to label the expression that I have to simplify and then do my work on the side here. So I'm just going to label 1, and I'm going to write out, we've got 3t to the power of 3 plus 6t squared minus 15t. So I'm going to factor this one separately. So this is sort of going to be my side work, and I'm going to put it back into the equation. So taking a look at this, I'm going to factor this thing. So first off, I notice that they have common factors. We have common factor of 3 and also a t. All of these terms have this in common. So we're going to factor out a 3 and a t, and we'll be left with t squared plus 2t minus 5. With that done, now we're going to try to do some sum and product. So taking a look at just this part right here. So we need two numbers that multiply to -5 and add to 2. So if you think about what those numbers are, well, the only numbers that multiply to -5 are 5 and 1. So -1 and 5, or -5 and 1, and neither of those add to positive 2, which means we can't factor this any further. So this is actually fully factored, and we're going to replace it back into our equation. So we're going back into our original equation. I'm going to replace this guy up here with our newly factored equation. So we have 3t times t squared plus 2t minus 5 all over 3t. And if you notice, everything on the top is factored. So we have our two factors. Here's our first factor. Here's our second factor. They're multiplying, so we know that they're factors. And then we have our two factors down here. We have 3t, or you can consider it 3 and then t. So we have a match. We have a 3t up on top, we have a 3t up on bottom, so 3t times 3t, that's going to be 1. So we are going to be left with t squared plus 2t minus 5. So this is the simplified version of this guy right here. So this looks like a nightmare to graph, but this one looks pretty simple because we can see that this is just a parabola. So these two will look exactly the same almost because we have this t at the bottom of this rational function here. And so therefore, because we have a variable at the bottom of the function, in the denominator, we know that there's going to be a restriction on t. So these two graphs are going to look exactly the same, except there's going to be a hole right where t is equal to 0. So we've got to also list our restrictions. So we're going to put a comma, but t is not allowed to equal 0. So one more time, these two rational expressions are equivalent as long as we also include the restriction. Let's take a look at the next guy. So we're going to simplify this as much as we can. Taking a look at the numerator, there's only one term. It's a monomial, so there's nothing to factor. Down here we have a very simple common factoring that we can do. So let's do that really quickly. I don't need any sort of workspace on the side this time. So we have 5x. We're going to take out the 5 and we'll be left with x plus 4. So taking a look at the factors on the top, we have 5 and we have x. And then down here we have 5 and then x plus 4. So we do have a match. 5 and 5 are factors of both the numerator and the denominator. So those are going to cancel out when we divide one into the other. And we're going to be left with x over x plus 4. So these two expressions are equivalent, except we're missing the restrictions. So I'm going to take a look here. Here it's harder to see where the restrictions are. It's harder to guess the value of x so that this denominator is equal to 0. It's easier to guess it once we factored. So if I take a look at this part here, I can see if x is equal to -4, then the entire denominator will equal to 0. So we're going to include a restriction that x cannot equal -4. And again, how I did that is I just set this factor equal to 0. So I said x plus 4, it cannot equal 0. And I just solved for x, so x cannot equal -4. Okay, let's keep going with simplifying. So I have two different expressions here. So I'm going to label one of them 1 and one of them 2. And they create a rational expression. So let's factor them on the side here. So I'm going to start with number 1. We have 7x squared minus 21. And the only thing we can do with this, because it's not a difference of squares, 7 isn't a perfect square, 21 isn't a perfect square, is we have a common factor. So let's take out the 7, and we're going to be left with x squared minus 3. Now let's take a look at our second equation here, and we're going to factor it on the side here. So number 2, we have 14x cubed minus 42. And again, these are not perfect squares. Either is x cubed. So all we have left to do is just to common factor, and 14 goes into both. So we're going to take out a 14, and we're going to be left with x cubed minus 3. So now we're ready to put it back into our function. So let's rewrite this guy on the left. So we have our first equation, and our first equation is just equivalent to the expression 7x squared minus 3. And then we have our second equation, which is equivalent to this guy down here. We have 14x cubed minus 3. So it is so tempting. These look so similar, but are they exactly equal? And the answer to that is no. X squared minus 3 is not the same as the factor x cubed minus 3. So I can't do anything about that. But I can do something about the 7 and the 14. If you just sort of isolate the 7 over 14, we know that if I were to simplify or reduce the fraction 7 over 14, well, I could divide 14 by 7, so divide by 7, and I could divide 7 by 7, and I would be left with 1x squared minus 3 all over 14 divided by 7 is 2x cubed minus 3, and that's my final simplified expression. If you don't want to include the 1, you could just do a final step of just saying x squared minus 3 all over 2 bracket x cubed minus 3. And that's fully factored and simplified as much as possible. So this expression is equivalent to this expression only if we add those restrictions. So we got to start taking a look. Remember the numerator, that's allowed to be 0. There's no restrictions on the numerator. So let's continue down our work and take a look at what the restrictions on x are. So here it's not factored, so it's very difficult to see. Here we can see that there is a value that x can't be. We just got to figure out what it is. So I'm just going to write our restrictions on the side here. So we know that x cubed minus 3 cannot equal 0. So we just got to solve for this. So I'm going to bring this negative 3 onto the other side, and we have x cubed cannot equal 3. And now we've got to get rid of this cubed. So we can do that by cube rooting both sides. So we do cube root of both sides. And these two are going to cross out, and we're left with x cannot equal the cubed root of 3. So there, that's our only restriction. So I'm going to add to our final expression that is equivalent to x squared minus 3 over 2x cubed minus 3, as long as x does not equal the third root of 3. Let's continue with the next ones, and now I'm going to leave you to do the factoring. So taking a look at the numerator, we can't factor that anymore, but the denominator we can. So do your side work and go ahead and start the video once everything's factored. So once you have everything factored, this bottom expression should factor to m minus 3, m minus 2. And so we have one factor up top. So it's not m or 2, it's m minus 2. That's considered one factor. And then we have two factors at the bottom, m minus 3, m minus 2. So again, I added these brackets so it's more clear. M is not a factor. 2 is not a factor. M minus 2 is the factor on the top. As well, we also have a 1. We always have an invisible 1 there. Okay, so we have a factor in common. We have m minus 2 in the numerator, m minus 2 in the denominator, so both of those are going to cancel out. What will we be left with in the numerator? Don't forget that there's a 1 there. So if we realize that we have got nothing left, we really do have a 1, and we're left with m minus 3 up at the bottom in the denominator. And then we got to look, these two are equivalent, except we have some restrictions that are missing here. So let's take a look. From here, it's very hard to see what m is not allowed to be, but here we can clearly see m can't be equal to 3 and m can't be equal to 2. So we're going to say that m cannot equal 3 and cannot equal 2. All right, so let's try E now. So go ahead and factor the numerator and the denominator on your own and then come back to the video. So now that it's factored, you should have something that looks like this. We have our numerator, maybe you've written it as x plus 2 squared, that's fine, and we have our denominator all factored. So we can see we have two factors that match. We have one x plus 2 and then another x plus 2 on the numerator and the denominator, so those are going to cancel out and make 1. So we're left with one of the x plus 2 factors at the top and one of the x plus 3 factors at the bottom. So now we know that this expression is equivalent to this one as long as we include the restrictions on x. So here it's very hard to see what x is not allowed to be. So let's take a look at the factored version. We can see that x can't equal negative 3 and x can't equal negative 2. So we're going to write that x cannot equal negative 3 and negative 2. So just as a side note, if we were to only look at this, it looks like the only restriction is x cannot equal negative 3. However, when we take a look above, we can also see that x was not able to equal negative 2. So just be careful not to just look at our final equation, but also take a look at the equations as we are simplifying them. So this one's a little bit of a tricky one. We just got to get a little bit creative. So we have a expression in the numerator, expression in the denominator, and neither of them can be factored. Like there's no common factor between 3 and x other than 1, as well as x and negative 3. So our problem is, how are we going to simplify this? Well, if you take a look, they're so similar, they're just slightly different. So we're going to do a little bit of manipulation. So if we factor out a negative 1 outside of this numerator, then we're going to be left with negative 3, that's what we have down here, and we're going to be left with positive x. And then we're going to see a common factor. So let's factor the numerator, 3 minus x, by just taking out a negative 1 and seeing what happens. So if I take out a negative 1, I'll be left with negative 3 plus x, and that's equivalent to 3 minus x. And then if I quickly rearrange this, I'm going to put the x first and then the negative 3 afterwards. I'm going to have negative 1 and then I have x minus 3. So if now I can see that we have factors that match. So I'm going to put them back into this equation. So instead of 3 minus x, I'm going to write negative 1 x minus 3, and then in our denominator was always x minus 3. So again, x is not a factor, negative 3 is not a factor, x minus 3 is the factor. And we can see now we've got matching factors, and we can cross them out, and we will just be left with negative 1. So we can say that these two expressions are equivalent, except that there's restrictions on the denominator. So there's restrictions on the value of x, and we know that taking a look down through our calculations, the only thing x cannot equal is positive 3. So what this negative 1 means is if we were to add, let's say we were to say that f at x is equal to this, what we're saying is that our final equation is y is equal to negative 1, which is just going to be a horizontal line, but we're going to skip over the point where x is equal to 3. So our final answer is that this is our simplified expression, which is equivalent to this one, as long as x is not equal to 3. Okay, let's work on our final example. So here we've got two ugly expressions in the numerator and the denominator. I can see that there's nothing that I can factor out of the numerator in terms of common factors, as same with the denominator. So I'm left with decomposition for both of them. So I'm going to label one of them 1, one of them 2. I'm going to factor them on the side. So you do the same and then come back to the video and we'll see if we have any common factors that can cancel. So once you've got everything factored, our first expression should factor to these two binomials, and our second expression should factor to these two binomials. If you notice that yours are different, so your numbers are different, just take a look at the work over here and check out where your mistake must be. So when we take a look at this, we have two factors on the top, two factors at the bottom, and we do have matching factors. 2v plus 3 and 2v plus 3 are equal, so when we divide them, we will get 1. And so what we'll be left with is 3v plus 1 all over 2v plus 1. So some students will take a look at this and say, okay, miss, plus 1, those must cancel out. But what have we done wrong if we do that? Well, this is not factored. This entire thing is a factor. This entire expression is a factor here. So plus 1 is not a factor. 3v plus 1 is a factor. And we have these invisible factors of 1 multiplying against it. So we're going to leave this exactly how it is. So this is factored as much as possible and simplified as much as possible. So these two expressions are equivalent, except that we have certain restrictions on x, and we got to figure out what those restrictions are. So these ones are a little bit harder to see. So I'm going to do a restrictions section down here. We're going to figure this out. So if we take a look from here, almost impossible to pick out what the v's are not allowed to equal. So let's go to the factored version. So we have a restriction from this binomial and a restriction from this binomial. If you can see it in your head, that's awesome. If not, because it's going to be a fraction, just bring it down here and we'll work it out. So 2v plus 3 cannot equal 0. So let's isolate for v. So I'm going to bring that plus 3 onto the other side. We have 2v cannot equal negative 3. And then I'm going to divide by 2 and divide by 2. And I'll be left with v cannot equal negative 3 over 2. So that's our first restriction. And then our second restriction will come from this binomial, 2v plus 1. So we have 2v plus 1. That also cannot equal 0. And so I'm going to send this plus 1 over. And we'll be left with 2v cannot equal negative 1. And we're going to divide by 2 and divide by 2. And we'll v cannot equal negative 1 over 2. So we have our two restrictions right here. So we're going to add them to our final equation. So these two equations are equivalent as long as x does not equal negative 3 over 2 or negative 1 over 2. And there's our final answer.